be right back.
Okay.
Oh,
Hey, Charlie.
What's up?
Not too much. Justin, you there?
yep.
All right. I'm gonna turn off my video here just because I don't know if that was the issue last week. So this week we aren't gonna be having anything that's really video intensive. So
Okay.
Well, I'd still like to see you.
yeah.
Throwing that out there.
Kate texted me earlier. She's got something that's going on at work. Her plant got shut down, so she's got to stay late to help get it back up, so she won't be joining us.
Okay.
Wes said to tell you, "Ooga booga dooga," something like that.
To tell me?
Yeah,
Okay.
not sure what he meant.
Me neither. So how's work going for everyone?
Moving
Good.
along.
Busy.
Yeah, it's been crazy
Shit.
at work for me too.
The real world, I guess.
Yep.
And James, I'm not gonna be able to make it to class next week.
Okay. Todd might not be able to make it next week either, right, Todd?
It's possible that I might not.
Okay.
I'll be here.
Good to know.
Throwing it out there.
What a scholar, Charlie.
Gentleman first, and then a scholar.
So, Wiki. Charlie, you had the intro, right?
Yes.
Alright. Todd, you've got the description. We can talk a little bit more. I know that you were having some issues with that. We'll talk about that after class. Justin, examples. I'm not seeing it.
Was I? Yeah, I did. Did I not save it? Hold on. I'm saving it right now. Recover
Okay.
draft. Draft.
Yeah, I kicked you off because you're taking too long.
What the hell? Hold on. This is a read-only view of your covered edit. Please close Windows. What the hell is going on? I literally typed it before class, and now it just didn't save. It said something about the edit wasn't saved.
Okay.
Hold on. Let me refresh.
One reminder, don't forget to be posting any web sources that you guys are finding for information that you're finding, even if it's, you know, just a general description, just kind of post it so that we can kind of find resources and go back to them.
Mm-hmm.
So other than that, I would like everyone to just continue emailing me their homework just so that I have a record of it.
Okay.
I realize that we discussed it in class. That'll be the first thing that we're talking about today, so just having that record for my sake later down the road.
Pretty sure Charlie messed up my edit. It says recover draft. We have your draft from your prior unsaved edit. However, the page has been edited since then.
I told you I
Like one of the
messed
options
up.
will proceed.
You
And
weren't
I'm
going
How
quick
convenient.
I click view draft and it says this big red bar across the screen saying it's pretty much gone.
Yeah, I kicked you off.
Charlie,
Hey,
I have a bone to pick with you.
pick your shit up, man.
James, I will redo that.
That's all right. Were you able to recover any of the information that you typed?
No.
All right.
It basically said that Charlie edited after me and he basically discarded it all.
All right.
That's my bad. I seen that I was gonna break link, and I broke it, but I didn't think it was gonna delete your information.
All right.
That's okay.
Yeah, Yeah,
I'll
he did.
check.
He told me beforehand. That's what
That was
he
just a
was
bonus.
I'll check in the next couple days if you just want to type it up again here.
Yeah, I'll do that.
So, not that big of a deal. So I suppose we'll start off with talking about the homework. This week's topic is how we utilize signals to identify unknown systems. First question of only two that I had for you guys last week was what type of signal do you think are most helpful in determining system reactions? So I don't know if we want to go ahead and go alphabetically. Will probably be easiest. So Charlie, if you want to start that discussion.
I thought, well, playing the devil's advocate, it's always dependent on the system, but most of the time I think that it's valuable to actually take readings first, find out which signals are independent of the rest of the system, so that you can take that information and remove it from so basically your process of elimination, getting down to the variables that are actually impacting the system, taking out the noise, basically.
Okay.
And then from there, you're able to start changing the parameters that actually have an impact on the system to have a better understanding.
All right. Justin?
Kind of like what Charlie said, and I guess I had experience with that on my magnetation project. We took a lot of data readings, and got a lot of signals, and it was mostly Cody and Case that analyzed them and took out all the noise and did all their transforms, whatever they did to it, to get what they could use to get what they wanted, I guess, out of it.
Okay.
But I know Kate typed that linear signals, if the signal is linear, a mathematical formula can be used basically to predict the reaction of that.
All right. Todd?
Well, I admittedly just saw that you emailed me the homework.
All
So,
right.
looking at that, most helpful in determining system reactions, I would think it depends on the system reaction. But, I don't have a lot of experience in that, but I can get that to you. I'm still trying to get caught up with the class,
Yep.
and so I can get through that for you. We could talk after.
All right. So what Charlie and Justin brought up are good points. You do have, when you're working with a system that's running, you do have a lot of noise. You have a lot of signals that you don't necessarily know where they're coming from, especially in determining an unknown system. Trying to kind of weed out what is noise and what isn't can be very difficult, and what your system truly is encompassing that you're reading. One of the ways to kind of mitigate that amount of noise is to actually use a delta function as your input signal. And just a reminder, the delta signal is just a single discrete point. So it's one point of data that you're going to read. So you're going to put that into your system and you're going to take it out, take the reading from that. And that's actually a good way to help remove that noise, because you know that there's going to be a specific change in your system when you add that signal. And anything that's the same between your input and, or your output before you put in your signal and everything after, that when they match up, all of that is the same. You can pretty much remove that. So,
Can you say that one more time?
So, in an unknown system, a good way to remove noise is by using the delta function, a single discrete point.
Yep.
The reason why it's useful is because prior to putting in that signal, you have a certain response that you can measure from your system that includes noise. After you put it in, you're going to have an altered signal. Everything that matches from the before and after adding that signal can be removed because they match up. They're the same noise signal. So all of those noise signals we can remove because they aren't being affected by the signal input that we're putting in.
Mm-hmm.
Is that the delta function?
Yep, that is the delta function, the single line discrete point. So does that kind of make sense?
Mm-hmm.
Yep.
All right. The other advantage to using the delta function is that you can shift it to different points in time, and each of those independent points you can then add to your graph. So it's analogous to taking multiple data samples from, say, you're reading something off an Arduino. The way that the Arduino actually gathers data is it takes multiple discrete points of data. So that's how we're pulling that information in.
Sampling.
And that's what we're plotting. So the delta function is probably the most useful. You can use other functions to kind of measure an unknown system. One example being a sonar device. Sonar works off the principle of you're putting sound waves, a signal, a known signal, into an unknown system. Let's say it's on a boat and you're trying to read the bottom of the ocean. Basically what you're doing is you're getting a feedback from that system. In the case of sonar, it's you're putting out analog, you're getting back analog, and your return is dependent on depth and material and things like that. But generally with sonar, you don't care necessarily about the depth so much. You're just trying to see what's there. So there are more advanced ways of getting like depth readings. So that's another signal for an unknown system. Can you guys think of, well, besides the sonar, any examples where we're putting out a signal to identify some factor of an unknown system?
X-ray.
X-ray, yep. So in that case, we're putting out X-rays, which are a wave to visualize bones and other things.
First thing I thought I had was a Vexilar. I kind of went over that.
You have MRIs, the same sort of thing.
Yep, different signal, but same concept. No, looks like Justin dropped out here. Let's see if I can add him back in. Ooh. There we go. Back, Justin?
Yep.
Alright.
Why does it keep doing that? Do you know?
I have no idea. It could be the connection between you and myself is bad.
Yeah. My Wi-Fi is not the greatest, so.
Yeah.
When you live in
Anytime
the
you're on
middle of a
Wi-Fi.
frozen tundra, I mean, it's not the greatest up here.
So.
It's not already frozen up there, is it?
Yeah, man.
It has been for like 3 months.
I had 33 today, but it didn't melt everything, so.
Really?
I'm kidding, Todd.
Wow. It's cold up there.
Anyway, back to class.
So. So the examples that have been brought up are X-rays and MRIs. Again, basically on the same principle of sonar. You're putting in a known wave and getting feedback from an unknown system. In the case of X-rays and MRIs, it's most often in the human body. Justin, can you think of any examples of putting a known signal into something to get into an unknown system to get a response?
I'm just thinking, like, would a microphone be one? Like, you're kind of giving the signal of your voice, the sound, into that, and it's somewhat reacting to it. I don't know.
In that case, you're basically recording an unknown signal.
Okay.
But doesn't a lot of those microphones and stuff have written information into it to cancel out like background,
cancellation.
low, say, echoes and stuff. So when is that kind of what?
It could be. I don't necessarily know how active noise cancellation works in microphones. Whether it's cutting, it could just be cutting out lower frequencies. Or it could be, like you're suggesting, taking the signal that's coming in, matching it over, and cutting out that noise.
Oh, I know. They can't see you.
Having fun there, Todd?
Can you see me?
Yeah, I can see you.
Wes says hi. I'm sorry, he's distracting.
I can see Wes. What?
Yeah, we work at the same place.
I got him the job, actually.
Holy shit! Two
Wow.
throwing that out there.
All right. Continuing where we kind of left off, kind of moving away from things that are a little bit more, or moving towards rather, things that are more accurate rather than MRIs and X-rays and things like that, where we're putting in a signal and we're just kind of getting a conglomeration. One way that we use signals, known signals, is actually in astronomy, light spectroscopy, understanding, it's basically the way that we measure the components in atmospheres, so like oxygen, nitrogen, CO2, things like that. In extraterrestrial planets, that's how we know the composition, say, of Venus's atmosphere. So basically the way that we do it is we can take sunlight, in this example, and we know the wavelengths of light in sunlight. That's our known signal. When it passes through an atmosphere, which is our unknown system in this case, you get deflections, which is the system is altering the signal, and we're getting a different signal back. We can actually take that and compare it to light passing through different gases, and in that way understand how those systems react and combine those to find out what the exact composition of an atmosphere is. So that's a very, very precise example of one way that we use a known signal and get a very precise answer back. So we took an electrical core competency and connected it to astronomy. So
I did not know that. That's pretty cool, though.
I was thinking about the same thing. Like, I know that you use sort of similar ideas to figure out what kind of rocks are in the ground, and I don't know exactly how that works, but based on something you could tell, like, is it what kind of rocks you're going to dig through, or that's where you want to be. It's probably sonar or something.
I know that in Curiosity, the Mars rover, they actually take soil samples and they vaporize it, to part of that being to try and see what the moisture content is, but also to identify what the soil composition is. So silicon, CO2, carbon-based elements, things like that. So that's another example.
That's cool.
So, coming back to real-world applications, LiDAR or radar guns work off of the same principle. We're putting out a signal, in this case a laser beam, that's actually discrete, almost delta functions. Not quite, because they have to be a certain length of laser pulse, but it gets close enough to be a good example. So we're putting out a lot of laser pulses that are hitting and reflecting off our vehicles, and there's actually a time shift that happens due to, or from the reflection. So light travels at a certain speed, we know that. It goes out, hits a vehicle, reflects back, and we can measure that.
Right.
And those times help us understand how the system, in this case being vehicle speed, vehicle and vehicle velocity, how it's changing. So that's an example of essentially a discrete signal being used to identify some component of a system.
So it's basically taking like a sample rate, and the rate that comes back is the velocity of the other vehicle?
Yep.
Okay.
So
I should have known that one.
So there's a lot of examples. A lot of errors that happen in music discs. Actually, there's some amount of correction that you get. So when you're playing a CD and it skips, there are ways of correcting that through digital means, just by kind of being able to measure and take the estimates around there. You're kind of getting a grasp of how the system is supposed to react, and then you hit an anomaly, you can kind of recreate a little bit how it should have sounded. At least digitally. So there again, it's a case of knowing your system, knowing how it's reacting. When you see anomalies, you can kind of trace them back to what's causing them, and seeing if you can correct them. So ultimately, that is the bulk of how we're actually going through. We've kind of covered the second question through this discussion, explaining how you might go about determining the reaction of an unknown system. Charlie and Justin, you both kind of alluded to that in your first answers.
Yeah.
So you're gauging what the system is putting out, trying to remove as much noise as possible, and then using discrete functions or known functions, you can actually go through and measure that response and get a much clearer response graph. Make sense?
Yeah.
That really is about the gist of what this topic entails. That I can readily explain. There's, I'm sure, more information out there. I know it's been a crazy week for me. I know it's crazy week for Kate right now. I'm sure it's been a crazy work for the rest of you. So if you guys want to take this time, Justin, I know that you want to take some time and finish out that chunk of information that Charlie corrupted.
The wiki, yes.
Hey, watch that.
Todd has some questions that he and I need to discuss, so
Yep.
Oh,
That sounds good.
research stuff for topic number 3, I believe. Have you guys found any information, any hiccups? Are you having any trouble with finding information? Topic number 3 is representing signals no, that's this week's. System properties, and how systems affect signals.
I have not looked at that yet.
Okay.
I mean, at my part of that yet. We've
Charlie?
probably gone over it, but a little bit.
The new homework?
The wiki homework, yeah.
I haven't gone over the new homework. I'm going to do that here probably tomorrow.
Alright. Like I said,
I can call you tomorrow and we can chat about it if you want.
I just wanted to know if there were any hiccups. If again, if you're finding any issues, if you're having some questions, feel free to shoot me an email. We can look through information together. So that's kind of what Todd and I are going to be doing. We're going to be looking through the information again, trying to gain a better understanding of it.
Okay.
So I will send out some homework. I will send out the assignments for this topic on the wiki, and we'll go from there.
Perfect.
All right.
Thank you, James.
Yep.
Bye-bye.
Bye. Alright. I've been recording, so I'm gonna stop recording this part, Todd.
Okay.